Distribution law. Nernst distribution law studies the distribution of a solute between two immiscible solvents in contact with each other. When a solute soluble in two immiscible solvent is added to a mixture of these solvents, the concentration of solute in both the solvent layers are different. In other words, the solute distributes itself in both the solvent. For example, when a dilute solution of iodine in water is shaken with carbon tetrachloride, the iodine distributes between two immiscible solvents. Iodine is about 86 times more soluble in carbon tetrachloride than in water. Due to higher solubility, most of iodine passes into CCl4 layer. In simple words, iodine is distributed between two immiscible solvents, water and carbon tetrachloride. Ernst in 1891 showed that when a solute is added to a mixture of two immiscible liquids, in both of which it dissolves, then it distributes itself between both the liquids in such a way that the ratio of concentration of the solute in both the liquid remains constant at constant temperature. However, this ratio is constant only when the solute has same molecular state in both the solvent. Solute neither undergoes association nor dissociation in both the solvent. The generalization put forward by Nernst is called Nernst distribution law. A solute distributes itself between two non-immiscible solvents in contact with each other in such a way that at equilibrium, the ratio of concentration of the solute in two layers is constant at a given temperature, provided the molecular state of solute is same in both solvents. If the solute X distributes itself between A and B, the distribution law is written as concentration of X in solvent A by concentration of X in solvent B. C1 by C2 is equal to K. The constant K is termed as partition coefficient or distribution coefficient. Factors affecting partition coefficient. Nature of solute, nature of liquid pair, temperature. Nature of solute. For a particular liquid pair, the different solutes have different solubility, hence the value of partition coefficient will be different for different solute at given temperature. It is clearly seen from the data given below. Water and benzene, benzoic acid, water and benzene, succinic acid 0.0274 and 0.096. Nature of liquid pair. A given solid has different partition coefficient in different liquid pair as shown in the table below. Water in ether succinic acid 5.423, in water and benzene succinic acid 0.096. Temperature. The solubility of a solute in a particular solvent changes with temperature. As the temperature is changed, the solubility of a solute in a given liquid pair also change. Therefore, the partition coefficient also change. The change in value of partition coefficient for 1 degree rise in temperature is known as temperature coefficient. However, the value of temperature coefficient is generally small. Table below shows the value temperature coefficient for some system. Acetic acid in water and ether 0.064, succinic acid in water ether 0.55. Experiment verification of distribution law. Solutions in iodine and carbon tetrachloride of different concentrations are shaken with water taken in different bottles. These are allowed to stand undisturbed till the two layers of the separate out. A known volume of CCl4 layer and aqueous layer is pipetted out and titrated against ethanol sodium thiosulfate solution, and the concentration of iodine is determined. The following result is from the distribution of I2 and CCl4 and what show the constancy of ratio of concentration in each layer, hence prove the validity of distribution law. 0.02, 0.0023, 86.95. These results show that C1 by C2 is almost constant, hence the distribution law is valid in this case. Conditions for the validity of distribution law. The distribution law is in the simple form K is equal to C1 by C2 does not hold under all conditions. Some limitations and conditions under which the law is applicable are as follows. Temperature should be kept constant. Solubility of a solute in both the liquid changes with the change in temperature. This may result in the change in concentration of both the solvents. Moreover, change in the temperature may affect the mutual solubility of the solvent. Therefore, with the change in temperature, a different value of partition coefficient is obtained at a every temperature. Hence the temperature should be kept constant throughout the determination of partition coefficient. The two solvents should be immiscible or sparingly soluble. The mutual solubility of two solvents should not be affected by addition of solute. The solution should be dilute. Distribution law holds good for the dilute solution. As the concentration of solute increased, the deviation from distribution law became more and more pronounced. The molecular state of solute should be same in both the solvent. When the state solute undergoes association, the law in the simple form is not applicable. This is when the solute undergoes association in any of the solvent. For example, distribution law does not hold for the phenol distributed between benzene and water because phenol undergoes association in benzene to form dimers. When the solute undergoes dissociation, the distribution law is not valid for the solute which undergo dissociation in any of the solvent. For example, electrolyte like HCl undergoes dissociation in water and its solution is a mixture of water and organic solvent benzene CCl4 CS2 does not obey distribution law in its simple form. Modification of distribution law with a change in molecular state. of solute. Nernst showed that the ratio C1 by C2 is constant. K is equal to C1 by C2 is applicable only when the solute has the same molecular conditions in both the liquid. That means the solute does not undergo association or dissociation in any of the liquid. However, if any change occurs takes place in one or both the liquid, then the distribution law gets modified. Let us consider cases in which a solute may associate or dissociate or enter into chemical combination with one of them. When solute undergoes association in one of them, suppose a solute X remains in the normal molecular state in the phase 1, whereas in phase 2 n molecules of X undergoes association to complex molecules. For example, solute X undergoes association in solvent 2, hence two equilibria exist simultaneously. X gives X phase 1, X and phase 2. Suppose the total concentration of solute X in phase 1 C1, total concentration of solute X in phase 2 C2. If alpha is the degree of association of the solute phase 2, then the concentration of associated molecules in phase 2 Xn is equal to 1 by Nc2 alpha. The concentration of normal molecules in phase 1 minus alpha C2. Applying distribution law to the distribution of X in two solvent, we can write concentration of X in phase 1, concentration of normal molecules of X in phase 2 is equal to K. C1 by 1 minus alpha C2 is equal to K. Applying law of chemical equilibrium to the polymerization process, Nx gives X, and we can write the equilibrium constant Keq as concentration of associate molecules in phase 2 by concentration of normal molecules in phase 2n is equal to K equivalent. 1 by Nc2 alpha by 1 minus alpha C2n is equal to K equivalent. Taking nth root on the both sides, n under root C2 alpha by 1 minus alpha C2 is equal to constant. Dividing equation 1 by 2, we get C1 by n under root C2 alpha K by K equivalent constant. However, when the molecules in phase 2 are completely associated, alpha is equal to 1, then equation 3 becomes C1 by n under root C2 is equal to constant. This relation is used in determining the value of n, the extent of association of the molecule. The values of C1 and C2 are determined experimentally and substituted in the equation 4. Putting n is equal to 1, 2, 3, the value for which a nearly constant value of K is obtained is equal to n. Equation 4 has been verified for studying the distribution of benzoic acid between water and benzene. Benzoic acid exists almost entirely as dimers C6H5COOH whole twice in the benzene, but in a normal state of water. Evidently, the ratio C1 by C2 is not constant, hence benzoic acid does not exist as single molecules in benzene. The fairly constant value of C by under root C2 shows that the benzoic acid exists as dimers in benzene. The method to calculate n has been explained in section 8.0. When the solute undergoes dissociation in one of the solvent, let the solute X dissolved in phase 1 in the normal state undergoes dissociation in solvent 2 as shown in figure 3. The two equilibria existing simultaneously are X undergoes X phase 1, X A plus B phase 2. Total concentration in X phase 1 is C1, in phase 2 is equal to C2. The degree of dissociation of solute in phase 2 alpha and the concentration of unassociated molecules in phase 2 is equal to 1 minus alpha C2. Applying distribution law, the ratio of concentration of solute in equilibrium 1 is given as C1 by C2 1 minus alpha is equal to K. On the other hand, when the solute is dissociated in phase 1 having degree of dissociation alpha and remains undissociated in phase 2, then partition coefficient is given by C1 1 minus alpha by C2 is equal to K. When the solute is dissociated in both the solvent, case 3, it is evident from the figure 4 that the concentration of the solute in layer 1 is C1 1 minus alpha and layer 2 C2 1 minus alpha, where alpha is the degree of association in the solute. The partition coefficient is given as C2 1 minus alpha by C1 1 minus alpha is equal to K. Case 4, when the solute enters into chemical combination with one of the solvent. Suppose the solute X remain in the normal molecular state in the solvent, but one molecule of X combine with n molecules of the solvent in phase 2 to form X and S molecules. Following equilibria exist simultaneously. X in equilibrium with X phase 1, X plus NS, X dot NS. At the concentration of solute X in normal state in phase 1 is equal to C1. The concentration of X in normal state in phase 2 is equal to C2. The concentration of solvent molecules in phase 2 is equal to C. Concentration of complex molecules in phase 2. Applying distribution law in equilibrium 1, we get C1 by C2 is equal to K. Applying law of chemical equilibrium 2, we get C by C2 into CS raised to power n is equal to K1. In dilute solution, the concentration of solvent in phase 2 is in excess, therefore its concentration CS remains practically constant. Thus, equation 2 takes the form Cc by C2 is equal to K1 into Csn is equal to K2. Apply adding 1 to both sides. 1 plus Cc by C2 is equal to 1 plus K2. C2 plus Cc by C2 is equal to 1 plus K2. Dividing equations, C1 by C2 multiply C2 by C2 plus Cc K is equal to K by 1 plus K2. C1 by C2 plus Cc K by 1 plus K2 is equal to K3. C2 plus C total concentration normal molecules and solvated solute molecules in phase 2. Therefore, equation 4 may be written as total concentration of solute in phase 1, total solution of solute X in phase 2 is equal to constant. It is evident that when the solvent molecules enter into chemical combination with solvent molecules, the distribution law does not get modified. However, there is change in the numerical value of the constant. Normal C1 by C2 K. Normal associated C1 by n under root C2 is equal to K. Normal dissociated C1 by C2 1 minus alpha is equal to K. Normal combined with solvent C1 by C2 plus Cc is equal to K by K1 plus K2. Thermodynamic derivation of the distribution law. Derivation of the distribution law form the thermodynamics is based on the condition that in a phase equilibrium between two immiscible liquid containing the same solute dissolved in them, the chemical potential of the solute must be same in the both phases. Suppose the solute is present in two immiscible solvent A and B in contact with each other. The chemical potential in solvent A is UA and in solvent B is UB. At equilibrium, the chemical potential solute in both phases are UA is equal to mu B. From thermodynamics, we know chemical potential of the substance is given as mu is equal to mu naught plus RT ln A, where mu naught is the standard chemical potential and A is the activity. Mu A is equal to mu naught A plus RT ln A. UB is equal to mu naught B plus RT ln AB. UA plus RT ln A. UP plus RT ln AB. RT ln AA by AB is equal to mu naught B minus mu naught A. Ln AA by ln AB is equal to mu naught B minus mu naught A by RT. At constant temperature, the standard chemical potential mu naught A and mu naught B for given solute in a particular solvent are constant. Since R is constant, it follows the equation 5 ln AA by ln AB is equal to constant. AA by AB is equal to constant. Since the solutions are dilute, therefore the activities are equal to the concentrations. So equation becomes 7 become A CA by CB is equal to constant. Okay, this is the Nernst distribution law. It is applicable in this form when the solute is normally distributed in both the layer. However, it gets modified in the cases when the solute undergoes association, dissociation, or entry into the chemical combination with one of the solvent. Application of the distribution law. There are many applications of the distribution law in laboratory and in industry. Some of these are briefly discussed here. In calculating solubility of a solvent, when a solvent is shaken with two immiscible solvents in contact with each other at equilibrium, both the solvent are saturated with the solute. Therefore, the concentration at equilibrium are equal to the solubility of the solute in both the solvent. C1 by C2 is equal to S1 by S2 is equal to K. C1 is equal to S1, the solubility of the solute in solvent 1. C2 is equal to S2, the solubility of the solute in solvent 2. However, knowing the value distribution constant K, the solubility of solute in one of the solvent, the solubility in another solvent can be calculated. Distribution cut indicator. The certain solvent can appreciably dissolve even the small amount of solute present in some other solvent. When such a solvent is added to a dilute solution of the solute in some other solvent, most of the solute get distributed into the solvent. Hence, it acts as an indicator for the presence of even a small amount of solute. For example, a dilute solution of iodine in water is almost colorless. Iodine is considerably soluble in CS2. The distribution coefficient between CS2 and water is 400. Therefore, an extremely dilute solution of iodine can be estimated by adding a few drops of CS2 to its aqueous solution. A sufficient amount of iodine passes into CS2 layer and gives it a deep violet color. This solution may be treated against hypo solution till the violet color in CS2 layer disappears. Hence, CS2 can serve as distribution indicator in the iodometric titration in which iodine is produced during titration. In determining the extent of association or dissociation of a solute in a solvent, using distribution law, molecular state of a solute in a solvent can be determined. In the distribution experiment, if the ratio of concentration of solute in both the solvent C1 by C2 is constant, then the solute behaves normal in both the solvent. When a solute X undergoes association in one of the solvent, and X gives an Xn having consistency 2 in it, then the distribution law notifies the C1 by n under root C2 is equal to K. From the value of n, the molecular mass of the solute in the solvent can be calculated by multiplying the actual molecular mass by n. For example, the benzoic acid in a mixture of water and benzene exists as dimer in benzene, hence the value of n is equal to 2. Therefore, the molecular mass of benzoic acid in a benzene is 2 into 122 is equal to 244. By the value of n, above expression can be calculated by one of the following method: by hit and run method. The values of C1 and C2 are obtained experimentally. C1 by n under root C2 and is equal to K are put in the following equation. Then putting 2, 3, 4, the corresponding values of K are calculated. The number which gives a constant value for K is corrected value of n. Logarithmic method. We have equation C1 by n under root C2 is equal to K. C1 by C2 1 by n is equal to K. C1 is equal to C2 1 by n K. Taking log on both sides, log C1 is equal to 1 by n log C2 plus log K. Put to experiment value C1 C2 and C1 dash C2 can be write log C1 is equal to 1 by n log C2 plus log K. Log C1 is equal to 1 by n log C2 plus log K. On subtracting equation 2 from equation 1, we have log C1 minus log C1 dash is equal to 1 by n log C2 minus C2 dash. N is equal to log C2 minus C2 dash and log C1 minus C1 dash. Hence n can be calculated. Similarly, when a solute dissolves in one of the solvent in which its concentration is C2, but then the distribution law is applicable as C1 by C2 1 minus alpha is equal to K. Thus, the degree of dissociation alpha of the solute known at one concentration, the value of alpha at any the concentration can be obtained using above equation since K is constant. In the study of chemical equilibrium involving formation of complex ion, an important application of the distribution law is to study the equilibrium complex. Consider some reaction involving K formation of complex ions. Ki plus I2 is equal to Ki3. I negative plus I2 gives I3 negative. KBr plus Br2 gives KBr3. Br negative plus Br2 gives Br3 negative. Complex ions CuSO4 plus 4NH3 gives CuNH3 4SO4. Cu2 positive plus 4NH3 gives CuNH3 2 positive complex ion. Using distribution law, the equilibrium constant of any of these reactions can be calculated. On the basis of constancy in the value of equilibrium constant, the formula of complex ion can be found out. The application of distribution law in determining the formula of ion complex and I3 negative is described as follows. The solution of iodine in CS2 is shaken with water to determine the distribution coefficient of iodine between CS2 and water. A solution of iodine in CS2 of known concentration, say a moles per liter, is shaken with an aqueous solution of Ki of known concentration, say B moles per liter. After equilibrium is established between two layers, the concentration of iodine left in CS2 layer is determined volumetrically by treating an against sodium thiosulfate solution. The equilibrium constant is calculated as follows. The initial concentration of iodine in CS2 layer is equal to A moles per liter. Initial concentration of Ki solution is equal to B moles per liter. Distribution coefficient of I2 between CS2 and water is equal to K. Concentration of I2 left in CS2 layer is equal to C moles per liter. In aqueous layer, I2 reacts with Ki. Therefore, total concentration of iodine in aqueous layer will be much larger due to the formation of soluble Ki3. Total concentration free plus combined aqueous layer. Initial concentration of I2 in CS2 minus concentration of I2 left free in CS2 layer, A minus C moles per liter. Concentration of free I2 in aqueous layer can be calculated according to the distribution law. Concentration of free I2 in aqueous layer by concentration of I2 in CS2 layer. But the concentration of I2 in CS2 layer is equal to C moles per liter. Concentration of free I2 in aqueous layer, Kc moles per liter. Concentration of hydrogen combined with Ki, A minus C minus Kc moles per liter is equal to D moles per liter. According to the reaction, Ki plus I2 gives Ki3. Number of moles of I2 combined is equal to number of moles of Ki combined, number of moles of Ki3 formed. Concentration of Ki3 in aqueous layer, D moles per liter. Concentration of Ki in aqueous layer is equal to B minus D moles per liter. Concentration of aqueous layer, Kc moles per liter. Applying law of chemical equilibrium, we can write K dash Ki3 by Ki I2. Taking different initial concentration of I2 and K solution, the value of K dash is calculated for each side. The constancy of each value of K dash shows the formula of complex Ki3 that of complex ion is I3 negative. In the process of extraction, another important application of the distribution law in the process of extraction, the laboratory as well as in industry. In laboratory, it is frequently used for the removal of a dissolved organic substance from aqueous solution with solvents such as benzene, ether, chloroform, carbon tetrachloride. Advantage is taken out of the fact that the partition coefficient of the most of the organic compound is largely in favor of organic solvent. In industry, process of extraction is used to remove impurities from the product. The aqueous solution of substance to be extracted in shaker with an organic solvent is the highly soluble. After shaking vigorously, the mixture is allowed to stand for some time. The two layers are then separated using a separating funnel. The organic solvent is recovered by the distillation and used again for the extraction process to be more efficient. Following conditions should be fulfilled. Distribution coefficient of the substance between the extracting solvent and the solvent in which it is already dissolved should be very high in favor of extracting solvent. Sometimes the distribution coefficient in extracting solvent is artificially increased by the making the substance less soluble in aqueous phase. This can be done by adding some substance which decrease the degree of dissociation of the compound. For example, acetic acid, which weakly ionizes in the aqueous solution, is to be extracted with the ether. A strong acid, say HCl, is added to the solution. Due to the ionization of HCl, the H positive ion concentration increased. Due to the common ion effect of the ionization of CH3COH suppressed. As a result, there is a concentration of unionized acetic acid, hence greater amount of acid will be extracting in the ether layer. Similarly, the extraction of the organic base from its aqueous solution into an organic solvent can be increased by adding strong inorganic base. In general, the solubility of the organic compound in water can be decreased by the adding salt, hence distribution coefficient increase in the favor of extracting solvent. This is termed as salting out effect. Thus, we conclude that greater the distribution coefficient in favor of organic solvent, greater will be the amount extracted. To recover maximum amount of substance, extracting solvent should not be used in one lot. Rather, it should be used in maximum number of solvent. This is called multiple extraction or multiple step extraction. This fact that it is more efficient to use extracting solvent in small portion rather than lot illustrated. Suppose Ag of the solvent present in 1 liter of aqueous solution. We extract the substance with ether as the distribution coefficient of the substance between ether and water, and we are provided with 1 liter of ether which may be used in lot 2 installment 500 cc each. Using all ether in one installment, let x gram of substance extracting in the extracting solvent, then the amount of substance left in aqueous layer A minus x. Concentration in ether x by 1000. Concentration of water Ax by A minus x by 1000. According to the distribution of C ether by C water, x by 1000 divided by A minus x by 1000 is equal to 2. X is equal to 2 by 3, 0.67 in. Thus, only 67% of the total amount will be extracted. Extraction using 500 ml of ether. Let x1 gram of substance be extracted in the first installment of 500 ml ether. Thus, the concentration in ether is equal to x1 by 500. Concentration of in water is equal to A minus x1 by 1000. C ether by C water is equal to 2. X1 by 500 by A minus x1 by 1000 is equal to 2. X is equal to 1 by 2. 50% of the substance will be extracted in one installment. The substance left is equal to 1 by 2A. Now, 1 liter aqueous solution containing half Ag of substance is extracted with 500 ml. Let x2 be the number of grams be removed from the aqueous layer into 500 ml ether. Concentration of in ether x2 by 5 and concentration in water 1 by 2 m minus x2. C ether by C water x2 by 500 by 1 by 2a minus x2 by 1000 is equal to 2. X2 is equal to 1 by 4a. Hence 25% is extracted into ether layer. Total amount of substance extracted 75%. Thus, when the substance is extracting using 500 ml portion of the solvent, the percentage extraction increases from the 66.66 to 75. Similarly, it can be shown that using the same 1 liter of the solvent in 4 installments of 250 ml each, 93.175 of the substance given quantity of solvent in small portion. However, it must be noted that it is not possible to extract whole of the dissolved substance. However, large number of extraction may be carried out. Every time the substance distributes itself from two solvent and some amount is left. General formula for substance left. General expression to calculate the amount of substance left unextracted after a given number of operation is derived. Suppose W gram of the substance is present in V ml of the solution made by using solvent A. Coefficient of the substance between A and B. Let W1 gram of the amount of the substance left unextracted in the solvent A after first extraction. The distribution coefficient at the first stage is given as concentration of the substance in original solvent A by concentration of substance B. W1 by V by W minus W1 by V is equal to K. W1 is equal to KVW minus KVW1. W1 is equal to KV plus V is equal to KVW. W1 is equal to KV by KV plus V W. Now after the second extraction, W2G is the amount left unextracted in the solvent E. Then the amount of the substance extracted is W1 minus W2. From distribution law, W2 by V by W2, W1 minus W2 by V is equal to K. W2 is equal to W1 KV by KV plus V. Substituting value of W1 from equation 1, we get W2 is equal to W KV by KV plus V into KV by KV plus V. W is equal to KV by KV plus KV ka square. In general, the amount of substance that remain unextracted after nth extraction will be Wn is equal to W KV by KV plus Vn. To make extraction process most efficient, Wn should be smallest possible. This can be happen. The term KV by KV plus V is made as small as possible. In this term, the denominator KV by plus KV is bigger than numerator KV, hence the factor KV by KV plus V is less than 1. Therefore, factor KV by KV plus Vn will be the least for the greater value of n. Hence, the efficiency of the extraction increased by increasing the number of extraction using only a small amount of extracting solvent each step. Thus, it is obvious that better efficiency can be achieved by keeping very small and large. So it follows that the multi-step extraction is more economical than the single-step extraction. Also, it is clear from the equation 4 V can never with 0, however large value of n may be. That is not possible to extract a whole of the dissolved substance, however large number of extraction may be carried out. Every time the remaining substance distributes itself between the two solvents according to the distribution law. The principle of multi-step extraction is applicable to the washing of precipitate. In the repeated washing of precipitate with small quantity of solvent, the impurities are extracted to a large extent. The principle of extraction is used in Parkes process for desilverization of lead. Silver is more soluble in zinc than in lead. The adjunct lead is melted and heated to 880 degrees Celsius, and the molten zinc is added. Molten zinc is immiscible with molten lead, hence form two immiscible liquids in contact with each other, and silver behaves as a solute which is more soluble in zinc than lead. The partition coefficient of silver in favor of zinc is 300. Silver therefore passes readily from the heavier lead to the lighter zinc, which is then separated by repeating the process 3 to 4 times. Almost the entire amount of silver passes into the zinc layer, hence most of the whole of the silver can be extracted from argentiferously. In the determination of degree of hydrolysis, hydrolysis is defined as a process in which water reacts with salt to form an acid and a base. Hydrolysis is constant. A general hydrolysis reaction of a salt Ba can be written as Ba plus H2O gives Ha plus BOH. Applying law of chemical equilibrium, K is equal to HaBOH divided by BaH2O. Since the concentration of water H2O is very large, it is regarded as practically constant. Thus, expression may be written as HaBOH by Ba is equal to KH2 is equal to KH, where KH is the hydrolysis constant. In expression 2, Ha and BOH are the molar concentration of acid and base produced, and H is the molar concentration of anhydrolysed salt. And the above expression can be written as KH free acid free base by anhydrolysed salt. Degree of hydrolysis. Degree of hydrolysis of a salt may be defined as a fraction of total amount of salt which is hydrolyzed at the point of equilibrium. For example, in an aqueous solution of aniline hydrochloride, 80% of it hydrolyzed into aniline hydrochloric acid, then the large degree of hydrolysis is 0.80. The degree of hydrolysis is represented as H. Mathematically, H is written as number of moles of salt hydrolyzed by total number of moles of salt. Expression for degree of hydrolysis of different salt. The salt of strong acid and strong base such as NaCl and Na2SO4 KCl KNO3 do not undergo hydrolysis. Therefore, for such salt, expression for KH and H are not written. These constant for the other three salts I discussed here. Salt of weak acid and strong base. The hydrolysis reaction of salt Ba is written Ba plus H2 BOH plus HA. The aqueous solution Ba and strong base which undergo complete dissociation, where HA being weak acid remains undissociated. Therefore, we can be write Ba plus H2O, B positive, OH negative plus HA, A negative plus H2O, OH negative plus HA. Thus, the salt of weak acid and strong base undergoes anionic hydrolysis. If the initial concentration of salt C moles per liter and H is the degree of hydrolysis, then we have A negative plus H2O, OH negative plus HA, C00, C1 minus HCH. Hydrolysis constant is given by KH is equal to OH HA by A, CH C1 minus HCH square by 1 minus H. If H is quite small as compared to 1, then 1 minus H is equal to 1. Above expression becomes KH is equal to CH square, H square is equal to KH by C, H is equal to root KH by C. The degree of hydrolysis of salt of a weak acid and strong base is inversely proportional to the square of its smaller concentration. Salt of strong acid and weak base. General hydrolysis reaction for the salt B is written as Ba plus H2O BOH plus Ha. The salt B and strong H are completely associated. Therefore, we can write B plus A negative plus H2O BOH plus H positive plus A negative, weak base. B positive plus H2O BOH plus H positive. Hence this salt undergoes cationic hydrolysis. In this case, hydrolysis constant is given as KH is BOH, H positive, B positive. C by C1 minus H, CH square by 1 minus H is equal to KH. As H is very less than 1, therefore above equation becomes CH square is equal to KH, H square is equal to KH by C, H is equal to 1 root KH by C. Salts of weak acid and weak base. The salt of weak acid and weak base B undergoes hydrolysis as Ba plus H2 BOH plus H. Weak acid base and weak base. Weak acid and weak base are weakly dissociated, but salt B is completely dissociated. Thus, we can written B positive plus A negative plus H2 BOH plus H. Thus, it involves cationic hydrolysis as well as anionic hydrolysis. At equilibrium, B positive plus A negative H2 gives BOH plus HA, C1 minus C1 minus 0 0 CH KH BOH HA, B positive A positive CH C1 minus H, C1 minus H square by 1 minus H square. H is very less than 1 minus H is equal to 1. Therefore, the above expression can be written as KH is equal to H square, H is equal to root KH. Hence, the degree of hydrolysis of such a salt is independent of the concentration of the salt solution. Application of distribution law in determining the degree of hydrolysis. Aniline hydrochloride is a salt of weak base and a strong acid. Its degree of hydrolysis is determined as follows. Determination of hydrolysis constant. Aniline hydrochloride is hydrolyzed according to the reaction. The hydrolysis constant is given by C6H5NH2 plus H2O free aniline. KH is equal to free aniline free HCl by unhydrolyzed salt. To calculate the above concentration, aqueous solution of aniline hydrochloric as of separate into two layers. Free aniline get distributed between water and benzene, while HCl and unhydrolyzed salt remain in the aqueous layer as shown. Determination of concentration free aniline in the aqueous layer. A known volume of benzene layer is taken out and the solvent is evaporated. The weight of aniline left behind is found. From this, the concentration of aniline in the benzene layer is calculated. The concentration of aniline in the aqueous layer can be calculated using distribution law. Determination of concentration of the free HCl in aqueous layer. From hydrolysis reaction, it is clear that number of moles of HCl set free is equal to total number of moles of aniline produced. For the total amount of aniline produced is equal to amount of aniline present in aqueous layer plus amount of aniline in benzene layer. Concentration of free aniline in aqueous and benzene layer is calculated in step 1 above. From these values, the number of moles of free HCl produced is also calculated. From the volume of aqueous layer, the number of moles of HCl, concentration of free HCl in the aqueous layer can be calculated. Determination of concentration of unhydrolyzed salt in the aqueous layer. Again, from the hydrolysis equation, it is seen that the number of moles of aniline hydrochloride hydrolyzed, total number of moles of free aniline or HCl produced. The quantity of RH can be calculated in the step 3 above. Therefore, the number of moles of aniline hydrochloride hydrolyzed is obtained. When this is subtracted from the initial number of moles of the salt, the number of the moles of unhydrolyzed salt can be calculated. From the volume of aqueous layer, the concentration of unhydrolyzed salt can be calculated. Substituting the values of in step 1, 2 and 3 and equation, the hydrolysis KH of the salt can be calculated. Calculation of degree of hydrolysis of aniline chloride. After calculating the hydrolysis KH for a solution of salt having concentration of moles C moles per liter, the degree of dissociation hydrolysis can be calculated using H is equal to under root KH by C. Thank you.